talk about simulated annealing, which is basically a technique very suitable for dealing with hard problems, specifically with combinatorial optimization problems. I will talk in a few minutes. And this work was done at Caesar Systems by Leandro Pablo, which is one of our mathematicians, as Leandro commented yesterday, and me, mainly. Not me mainly, but
you mainly.
We mainly. Well, first of all, we can distinguish between the whole set of problems between two rather big classes or groups. The ones that are easy, meaning that no matter how bad programmers we are, we can probably write an algorithm and compute a solution for an instance of one of such problems. And the other big family is the hard problems, only for good programmers. And inside this class, there's another subset that is composed by problems that are inherently hard, meaning that no matter how good an algorithm for dealing with such a problem we have, maybe almost surely that algorithm will take a lot of time. And when I say a lot, we will see that it's a lot of time. So you're interested here in, as I said before, optimization problems. An optimization problem basically consists on the function that we'd like to optimize, I mean minimize or maximize, and then as a domain or a solution space over which our function is defined. So these problems are hard because the domain is usually extremely large. In fact, sometimes it's infinite. So we have two choices, of course. The first choice is to analyze the entire space of solutions at the risk of dying before an algorithm for doing that ends, but with the certainty that getting the optimal solution. And the other option that we have is to explore some subset or some handleable subset of the solution space. The risk in the second choice is that we can end up with a suboptimal solution. So good criteria must be established for discarding suboptimal solution. We are interested here in optimal solution or almost an optimal solution. So I'm gonna be father in a few months. It makes me feel like a good algorithm. Well, just to exemplify how hard a problem can be, we can take the traveling salesman problem, which is in fact a hard problem and an inherently hard problem. Well, it belongs to a family of problems known as NP-complete. But this problem consists of a salesman that has to visit some cities with some restrictions. He has to visit each city once and only once, and he has to start and end at the same city. And he has to do it using the minimal distance possible. So this is just one of the possible paths. These are the cities. Well, we can suppose that the salesman starts at the city number 1 and then goes or visits the city number 2, and so on. So the total number of possible paths using 25 cities is 24 factorial. This comes from, well, it is equivalent of analyzing the secret permutations between 25 elements. So, anyway, this is the number of the total possibilities between our 25 cities. Now, suppose we count with a very good programmer that has written an algorithm capable of analyzing 1 million paths per second. And, well, considering the seconds, the amount of seconds per hour, the hours per day, and so on. And suppose we have a possibility of counting with 7,000 million computers available for us to compute our algorithm. So making the math, analyzing the 24 factorial possibilities will take roughly 2 years, right? So it is a very hard problem. In fact, let's see what happens if we just add one city to our set of cities. Approximately, it will take 50 years. If we have 27 cities, we will have, well, 1,500 years, and so on. So this is a hard problem. So what can we do? Optimization, when dealing with an optimization problem, we have a very known approach, which is called local search, that in fact does what I said before, that was the second option. I mean, explores some subset within the main space, and it starts with a particular solution, and then it jumps to a neighbor solution with a definition of neighborhood, and it basically compares the two solutions, and if the new solution improves, it goes on with the new solution. So the problem with local search is that it is very sensitive to local minimum or maximum, local optimum. I mean, it doesn't go to edges. It keeps a path just when the solutions explored optimize the previous solution. So what can we do? Annealing, what does incorporates is the following. Suppose we have the salesman problem, and this is just one path, and we, as in local search, can pick 2 random cities from a path, and then we can trace, or, well, cross the path between the cities, and we obtain a new possible path. This is just a way of obtaining a new solution from an existing one. This is the same as in local search. Of course, we compare our 2 solutions, and then we accept, of course, every improvement, but the news are that we can accept or reject with some probability, depending on a parameter, that is the temperature. I will say in a few moments what temperature means, or where that's what it comes from. But the thing is that we can accept bad solutions. That's another. We say that we accept a bad solution or reject. It's the same with some probability depending on the parameter named temperature. That's because annealing comes from a physical phenomenon or physical experiment that consists on melting a material and then gradually cooling it until it becomes solid again, with the property that the final state has an optimum. It is optimum in terms of the free energy. So the thing is that we have an idea of a temperature that we can gradually decrease. Suppose we start with a high temperature and then we decrease. So what we are doing here is playing with the probability of picking up a bad solution. So this algorithm can take more, probably better paths than the local search algorithm. So here's a picture of, I can just use a simulator. This is the main GUI of the simulator. I can put it into RAM. We have here the salesman problem, and we have 25 cities. We can start with a several random problem, and then we can put the algorithm to work. Well, at the right side, on the bottom chart, we have two curves. The red curve is a temperature curve. As you can see, the temperature starts at a certain point, and then it goes up, and then it gradually decreases. And the green curve is our cost function, in this case, the distance of the path. And a phenomenon that can be observed is that at higher temperatures, the green curve varies a lot, and then when we reaches lower temperatures, the curve stabilizes. That's why, because we are reducing with this process the probability of taking bad solutions. So the final stage can be viewed as a local search, almost. Well, here we have a result. I didn't see what was the initial distance, but we can.
It's in the graph.
Yes, it is here. Wow, roughly 289. So we obtain here a similar result. We started with a distance of 234 some units, and we end up with a distance of almost 100. So it is an optimum, or I know you have to believe me that it's an optimum, but it's very near to an optimum. So the thing is that the time required for this algorithm for reaching to that solution was very short when comparing it with 2 years, or roughly 2 years. So it looks like a pretty good approach. So I will speak now about an analogy that we can establish between the physical phenomenon of percolation and another physical experiment that you can perform at home, I guess. And suppose we have a recipient full of stones of different sizes, and suppose at the beginning they are distributed rather randomly, meaning that maybe we have little stones in the surface or above, with bigger stones, and so on. and then we inject some energy to the system. Suppose this is our system. We inject some energy. For example, we start shaking the recipient with some speed, or and then we gradually reduce the speed of the shaking. Well, the thing is that at the end, we will know that the space occupied by the stones, has been reduced, or what is equivalent that the empty space of the recipient has been augmented or maximized. This comes from the physical phenomenon of annealing. We can see this process as a sequence of states in which each state is just a configuration of the stones and position. Imagine we have a number for each stone and a position. And from one state to the next, we can think that some stones are moved, so randomly. So we can think of states as mutations of the first state. And when we reduce the speed in which we shape the can, we are minimizing the energy we introduce into the system. But what happened? The little stones are more likely to move because they need lower energy, but also because they can reach the spaces between bigger stones. So the result is that at the end we minimize the entropy. Entropy in terms of, in this case, suppose the volume of occupied by the stones. So we say that entropy decreases with controlled random mutations because we are randomly mutating the positions of the stones. So this is the main idea of annealing. Okay? So here's our motivation problem at Scissor System. We were looking for new ways of making two probability distributions to meet some even correlation. Probability distribution samples. Like in this case, for example, we have two probability distributions. Normal and a log normal, it doesn't matter. And we have here two samples, I guess 25 or 24 elements each. And looking for given correlation means that the correlation is calculated as the sum of some formula or count between pairs. So in order to change the correlation, we just change the order of samples, and then we obtain a new correlation. It's easy to see that we must reorder just one sample because otherwise we will be evaluating twice some combinations. So suppose we have two samples and they had a current correlation of 0.1, and we want they honor some correlation, for example 0.7. So what can we do? We can try with annealing. Remember that analyzing the total number of permutation goes up to approximately 2 years. So, as I said, we can apply annealing. And as I said before, one of the elements, the central elements of annealing is the mutation between solutions, or having one solution, we need to get a new solution in order to keep going on the exploration of the main space. Here's just the definition of such a mutation in this problem. We have the two samples, and we change the order of two random elements in the second sample, and then we have a new possible solution. So again, we accept all improvements and reject bad solutions with some probability depending on the temperature of the system. And well, the thing is that applying annealing to this problem behaves very well. In fact, in this case, we obtain this correlation between the two samples. And remember that V1 is 0.7. So I can swap to that problem. Well, we built this simulator, and we started to add new problems. The first problem, of course, is the correlation, but the others were just for fun. But here's the problem. In order to see the correlation, to graphically, we can plot the two samples using a cross plot. In one of the axes, we have the values of one sample, and in the other, we have the values of the second sample. And this is the trend line, and we have, they say that's the correlation. So suppose we set up a random, we are using here, I don't remember, but two probability distributions, one now normally and the other, I don't know, doesn't matter.
Maybe like in the slide, normal and log normal.
Okay. And
it doesn't matter.
Well, it doesn't matter. Well, here I enter the goal. The goal is just, well, the objective of our function, of the function we'd like to optimize.
There might not be a solution with that value.
Of course.
So you estimate something, and depending on the program, you know the ranges, I guess. And maybe for a normal and log normal, 0.7 is expected to exist.
No,
Yeah.
but with a set large enough, you can have a solution always.
Really?
Yeah, not always.
No,
Not always.
because
Not
it's
always.
rather
Because it's
makes
not
the size
the-
of the-
Sorry.
We want.
We can find later.
In fact, depending on the, I guess Pablo will know, but depending on the distributions chosen, it maybe exists a closed formula for calculating this stuff, or deterministic algorithm. So I can simulate the chart below shows just the trials or the movements of this algorithm at each temperature. So for example, at a temperature of 1, and so these are the champs. The champs are the movements of the algorithm from one solution to another solution. So I can leave this running and go back.
This is kind of, well, it's a search algorithm, so it's somehow similar to genetic algorithms.
Yes.
But in genetic algorithms, you follow many individuals.
Yes.
Here, do you follow just one?
Just one.
Okay.
That's the main difference, I guess.
Okay.
Right. I guess a population can be distributed randomly or not.
On how we start the population.
Yeah, how do we start?
That's
You could have like a mix, right, where you follow many at the same time.
You mean starting many annealing
parallels.
from many?
With many annealings in parallel. I don't know how that benefits the final result.
We can try it.
I don't know.
You would be exploring different parts of the
Right.
space.
Right. You start with different starting points and it takes you to the different.
But this is equivalent to start many algorithms with different initial
This is-
values. It is known that annealing is not very sensitive to initial solution.
Okay,
So it doesn't matter.
that's a good answer.
Well, let's go back to the presentation. There is some data we can benefit from that we don't need to calculate the correlation, the entire correlation again. That's because having a current correlation and a swap of two elements, we can calculate a new correlation, avoiding the whole correlation. It's just a detail. So here we have the uncorrelated data, and we have the final data. Here we don't have the trend line. And here we have the chart I explained before. Again, the first stage, these points means that we first melt the system. We increases the temperature until the system melts, and then we start cooling. The important thing is the mechanism of gradually decreasing the temperature. And again, the cost curve here jumps from one point to another very far, and then it becomes smoother. So, a little bit about the design of this little framework. It basically consists of three main elements or components. The first of them is the definition of the problem. We have a combinatorial problem class with a goal. In the case of correlation, we saw that the goal is our desired correlation. This is an abstract class. And then we have particular classes for particular problems, because the problem is in charge of defining the measure of the quality of a given solution. And well, in the case, for example, of the salesman problem, it defines a set of cities and a matrix of distances between the cities required for calculating.
Sorry, you
the
never
path.
came back to the other screen with the thing running.
And to see the result.
Okay. It finished.
Nice.
And well,
We found a good correlation. You should say that.
Good.
it's a success. It is a success.
The 450 is the number of steps, is it?
I'm sorry?
The 450 in the x-axis, is that the total number of steps?
Yes, it's the total number of steps.
So without an interface, it takes nothing time. I mean, it's immediate.
Nothing. Yes.
It's 450.
Isn't it?
In fact, the amount of steps is given by a lot of parameters. Not a lot, but many parameters that I will show later. But well, we have, as I said, concrete classes for concrete problems. salesman problem. This is another problem that roughly consists on placing boxes or rectangles, avoiding overlapping between them. I can show.
I think so.
I can show.
I don't know.
I don't know if it works or it reaches the solution that we can. It is called the box placement problem. Here we can set a random problem. I don't know why. But it should okay. We have here five rectangles or squares, I guess. And the first one is very small. Oh, it's okay. Okay.
Random is random.
Okay. The problem here consists on placing the squares in a way such that the whole area occupied by the squares is minimum. This is the problem. And well, we can define this as a possible solution, and then another candidate can be defined as moving randomly some of these squares between the local area occupied by the total squares. So we can, oops, well, it doesn't.
Too much heat.
Okay. Okay, I can make it to run, but I prefer to follow the presentation. So here we have the box problem, and then we have, for example, a correlation problem where X and Y stand for the two samples. And the other component of our framework is the Annealing algorithm itself that acts on a particular problem and has a cooler. We name this at first a cooler because our first approach, I guess, it was just decreasing the temperature, but after, I guess, we had the mechanism of melting, so the name might be changed after. So again, we have particular or concrete classes for concrete problems, and that's because the algorithm is responsible of well, it collaborates with the problem, but it's also responsible of jumping from one solution to another, and there are some constraints between this kind of jump that has to be established in particular classes. So this is another, I don't know if 15 problem is in the other list, I guess it does. Okay, well, we have the 15 problem, so we have the 15 solver, the correlation solver, and we have rank correlation solver. This is another level of correlation that we have a system, and we like to improve this approach. And the STIDOR is the algorithm for solving the box problem.
The correlation is part of the product, right? It's embedded in the product today.
Yes, it is. It is.
The Annealing solution.
And in fact, this algorithm is working on the production version of the Entropy. Yeah.
Okay.
Sorry?
For a long time.
Okay. I meant the Annealing version.
Are you using multidimensional correlation? You have more than two variables related?
Not yet. Not yet. Okay, here's the cooling device, which is in charge of pacing the variation of the temperature. And as I said, it has many several parameters. For example, trials and jumps governs the amount of trials and jumps when we are locating a particular solution. So for example, if we have 10 trials and 5 jumps, the algorithm would try 10 times and it will jump only 5 if it happened to be the case. So we here have a simple pooling device with some parameters also, and we are using this. The thing is that annealing, as I said before, has 3 main elements, I guess. The first is the definition of mechanism of mutation, and the second is well, the probability that picking up a bad solution has, and the third element is the mechanism of changing the temperature. This is the, I guess, the key element of annealing, is the mechanism of gradually reducing the temperature. So there are a lot of parameters that comes from papers and books and a lot of stuff about how to decrease the temperature. So this is the 3 main elements: the problem, the mutator, because changes from one solution to another, and the cooler. So recall that I said before that we have we can classify easy and hard problems. There's an rather easy problem named n queens. This is not an n queen problem, and this is just for showing that annealing can be applied also to easy problems. This problem basically consists in placing n queens on a chess table and rearranging the queens or moving the queens, avoiding the situation in which 2 queens threaten each other. So I guess use the simulator again for, well, suppose we have 15 queens. And then we, first of all, I want to show you this is not all, but a few of the parameters we define for the cooling and heating stages of the algorithm. Where here's the kitchen, I guess. For when we are playing with some problem, we have to try with several combinations of these parameters, and that's the real work of studying a problem. So we try when we started dealing with correlation problems to figure out a suitable configuration of these parameters for a particular problem, and I guess we obtain. So I can run here this, go back. This is always solved by the algorithm. Here the mutation is given by just picking one queen and moving. Remember, I guess we just move the queens row by row. So the mutation consists on picking one row at random and then move the queen at the row to another position. And This is solution. And then we have just advantages and disadvantages that at this point we discover from this approach. Within the advantages, we found it very easy to implement from bibliography or our investigation. As I've shown you before, there are a few classes implementing this approach, and it is constraint friendly in that for some problems it is required to add some constraints in the way the algorithm explores the solution space. So it is easy to establish or to write down those constraints. And as I said before, also it is flexible and tunable, meaning that it has several parameters that you can play with in order to get better behavior. And the disadvantage is that it's the same. It is very tough for us. It was very tough for us. The part of trying with combinations of parameters, looking for better behavior, it takes some time.
Did you learn any heuristics to determine the parameters and stuff?
Do you simulate annealing?
Yeah, I was thinking about the same. Did you simulate annealing to find the parameters?
No, I think one of the conclusions was that there are many cooling devices, many algorithms to reduce the temperature, and the simplest one was the best.
Okay.
So there are many that are very common. You read the descriptions and they look great, they look perfect, you love them. So you spend time programming that fancy algorithm, and the simplest one is actually.
And with the imitator, that you have.
The imitator, should I answer?
Yes. Maybe 13.
Okay, he wants you to answer.
I'm sorry, what was the question?
I asked about the imitator, and if you have the same issues, the simplest one is the, I don't know, the beta. In the NP problem, you can choose how to move the queen, and you just choose to the row and to move some queen.
Yes.
It's very simple imitator.
We didn't study the n-queens problem a lot. We focused on the correlation problem, and there, I guess we didn't try with another mutation approach.
In general, the mutation is obvious, so you have to find a way to introduce a permutation. So it's a swap between two positions. So there is no, maybe there is another one. But there are cases where there are different strategies. For instance, with the boxes, you have to, the solution should avoid overlapping, but maybe your suboptimal solutions allow overlapping, and then you penalize overlapping in the cost of the suboptimal solutions in a way that is actually forbidden at the end. So maybe you have to think a lot about the mutation, because if you move a box to a random, totally random place, maybe that's not the best way. So there are different strategies.
Yeah, I don't know, but I think that you have to constrain that all possibilities should be allowed by the mutator. And
yes.
Also, there
yes.
should be a uniform distribution probably on the mutations. That is not trivial.
No, in fact, in the correlation problem, you can change not 2, but 3 elements, or in fact, n elements. Can be possible for picking up a new solution. So, well, at this point, we find it positive approach. So, that's all. I don't know if you...
You didn't show the result from the Queen
Así.
exercise.
Sorry, what?
No result.
Well, this is an easy problem, so the algorithm takes less time for solving it. So
It worked.
it works.
Thank you.
Igual no vamos a preguntar. No es
One last verification, especially for the Argentine, about this, is that in the soccer association here, they had a huge problem with the teams, with the fixing of the team, who will play against who. And because there are many constraints, because you cannot,
Yes.
I don't know, many constraints. Because
Independiente y Racing cannot play at the same time.
Teams that belong to the same neighborhood
Yes.
cannot be in the same place at the same time. So that problem was so hard that the AFA, the Soccer Association, had to hire a mathematician to solve that. And this mathematician wasn't able to solve the problem using traditional mathematics. So he learned about simulated annealing. So he implemented simulated annealing and solved the problem. This was about 20 years ago. So the Association of Argentine Football is still using that algorithm that is with annealing. And the mathematician, this guy, fall in love with annealing. So he started to use annealing to solve mathematical problems that were impossible to solve using conventional approaches. And he published several papers on pure mathematics using this.